Yuan Yao. Professor Yuan Yao is with the Hong Kong University of Science and Technology. Received his BSc, MSc in Control Engineering from Harbin Institute of Technology in China in 1996 and 1998. And MPhil in Mathematics from City University of Hong Kong in 2002. And PhD in Mathematics from University of California, Berkeley in 2006. Since then, he has been with Stanford University, and in 2009, he joined the Department of Probability and Statistics in School of Mathematical Science, Peking University, Beijing, China. He is currently professor of mathematical, chemical, biological engineering, and biochemistry, computer science, and engineering, Hong Kong University of Science and Technology. His current research interests include mathematical modeling for high-dimension data analysis and statistical machine learning with application in computational biology, computer vision, and information retrieval. Okay, thanks. Let's welcome Professor Yuan talk. Okay.
Okay. Thanks for Yan's introduction. I will try to give a fast talk because the time is delayed. So this is hopefully you can see this screen well. This is about the inverse scale space method for sparse learning, and mostly I focus on the statistical property. And maybe you heard those inverse scale space name before, or may not, but it's not so strange for you. Actually, you have been touching this kind of dynamics one or twice in applications in other scenarios with different names. Some people call it mirror descent. Some people call it linearized fragment. So anyway, let's see the detail. So here I would like to thank all those collaborators, and particularly today Tao and Xinwei and Yanwei, they all present their works. And so here, this is the content. So first I will try to give you some illustration or demonstration using R package and Python package. I think Yanwei already showed this DESI LBI Python package. Just show some very fast browse of these results to motivate what we are going to talk. And the second part, this is the most important thing. We want to show how the inverse scale space arise as a dynamics from lasso, very classical lasso, because lasso has bias issue, and to overcome the bias, then we can develop some differential inclusion dynamics. So
sorry, Professor.
Yes.
It seems that your on my side and your slides is still on the first page.
Oh, really?
Yeah, the title. I don't know whether it's. Oh yeah, yeah. That's good. Yeah.
Oh, I see. So maybe I cannot. Now, if I move, does that work?
Yeah. Yes.
This is a new page, right?
Yeah. Yes.
Okay, then maybe I just use this format. Maybe I cannot use the share full screen mode. That doesn't work. Okay, let's see this is the content, and I just now I say the second part is how the inverse scale space arise from lasso as a differential inclusion dynamical system. So this is a crucial part. And the next part is how the variable splitting was introduced into this classical inverse scale space, such that we can achieve some weaker condition for feature of variable selection problem. And this is how the DESI LBI, those type split LBI, those type of algorithm are derived. And that's the kind of the main summary. And now let's see the first package. This is our old package, CRAN-R package called the linearized Bregman algorithm, and mostly done by some former students before Ruanfeng. He is now soon to be the faculty in Northwestern University, and Jie Chao, he's a researcher in Tencent, and this is my old picture. And in this package, actually, we include several sparse statistical model that was widely used today, including some application like noise, outlier detection. So in this package, that includes the linear regression, and we are going to use inverse scale space and the linearized Bregman iteration. You will see in that, and logistic regression and graphical models. And we include two types of regularization like lasso and group lasso. And so this is the one line, maybe two line code for the central algorithm in this package. Just these two line codes. The first line is simply a gradient descent. Loss can be all the previous example we have mentioned. And the second line is a proximal map. So here we can use those penalty like L1 or group L1, or maybe something more complicated than that. And these are the parameters. Alpha case the step size, and kappa is a constant such that the product of step size and kappa with this Hessian matrix 2 norm must be smaller than 2 for stabilization. And this is looks like in the first side, looks like very similar to ISTA, iterative source thresholding algorithm. However, you will see soon that this algorithm have very different limit dynamics. What I mean by limit, I will show you soon. And for linear regression, actually, we can do this kind of linear regression model, use some group penalty or ungrouped, that's plain L1. So we apply this, you can use this line in R to apply that to diabetes data, which is very popular in statistics since Bradley Ifron first published paper based on this data. And here, this is the, if you are familiar with a statistical learning textbook, then this picture is looks very familiar to you. The top left is the lasso. We call the lasso regularization path. X-axis is normalized to be each of the beta, its absolute value, the absolute value of the coefficient divided by the max of beta 1 norm. And this is the normalization. And if the curve actually appeared early, like these two green curves, that means that these variables are very important, will be selected earlier than the late variables. So that's the lasso regularization path. The variation, the x-axis, the change is due to the lambda or regularization parameter change, although we use some different normalization as the different coordinates as the x-axis. On the right, this is called the inverse scale space method using the L1 penalty. So you can see the curve are very different to lasso. However, the order of those variables becoming to be non-zero bear a lot of similarity with lasso. So still the green curve appeared earliest than others. They are the most important variables. And below we call that's linearized Bregman iteration. That's the two-line algorithm I showed you just now. And basically you can see when kappa change from small to large, the curve shape may change. However, the order still very stable in terms of which one becomes non-zero first. So this is looks very interesting how this happened. And later we are going to tell you some story, but before that we can take some further example like logistic regression. Of course, this time we changed the model as well as the loss, but the penalty are still the same. And then if you apply this logistic regression to some real world example, so here is a data set we call the COPS winner publication called data set. So Professor Jiashun Jin from CMU collect 3,000 papers about 3,000 authors in the major statistical journals. And we select a subset of 382 papers. They are co-authored. They are authored by 35, include the author of 35 COPS award winner. That's the the highest prize in statistics. And this is the co-authorship network. You can see this graph is very sparse. The question is, can we model the co-authorship structure to predict whether in the future two authors would like to collaborate or co-author a paper or not? What's the probability? So this is the kind of question. And basically, we pick up one famous statistician, Peter Hall. Unfortunately, he already passed a couple of years ago in the pandemic season. And we pick up this Peter Hall, that's the, say, target response variable. And we ask how the other COPS winner scholars collaborate with Peter Hall. And the right picture is the co-authorship network. You can see Peter Hall only collaborate with 3 people, 3 scholars in the data set. Jianqing Fan and Tony Tsai and Carroll, RJ Carroll. So if you run a logistic regression with all the other authors target to Peter Hall as the response, you can see this kind of curve. The x-axis represent the solution path, the iteration. That means if you iterate this algorithm, you will basically see those curves along the iteration. And the particular 3 curves, those 3 color curves, that's exactly correspond to the 3 collaborators, Jianqing Fan, dash right here, and Tony Tsai, the dotted red here, and another is Carroll, Raymond Carroll, that's the purple curve here. So they are kind of leveled, appear to be non-zero very early, and becomes leveled, showing that these 3 curves will be true collaborators. And all the other curves actually can be arbitrarily small if you iterate. That means they tend not to collaborate with other, also tend not to collaborate with Tony, with Peter Hall. So this is an interesting logistic regression with the regularization path using our algorithm. If you are not that clear, maybe we can do a more complicated model. We ask the pairwise interactions from all the data. So this is called the Sparse Ising model, a statistical physics model. And in this Ising model, the likely probability of P authors, whether they co-author a paper, subject to this probability model. And HI measures the mean rate, and JIJ describe the interaction between XI and J. So if we ask whether 2 authors collaborate, then basically we ask whether JIJ is +90 or not, the sparsity of J. So we say if JIJ is larger than 0, then that means also I and also J tends to collaborate more often than others. Otherwise, if less than 0, then they tend to less collaborate or collaborate less frequently. And if they just equals to 0, that means these 2 co-authors does not have interaction. So if you look at how this algorithm works on this model, here is a simulation. Simulation means we generate the data using a 2D grid Ising model. And on the right, we try to use this algorithm using such simulation data, try to recover this grade. So this is a movie. Just be patient and let me click. You can watch what will happen. So you can see lots of the 2D grade will be rapidly formed during the iteration. And if that will be stable. If you wait further, then there will be some light lines which are crossing different large scale interaction. But those are not true interactions because we know the ground truth model must be on the left. And if you see this right model learned during the iteration, that means that you learn some fake interactions or noisy interactions. So this is how we illustrate this algorithm. If that iterates, somehow the dynamics will first give the true signals or true interactions and then learn the noise or generate the fake interactions. And we want some sparse model along this iteration process. That means we want to model the true interactions, then we need some early stopping. So this is the intuition behind how this algorithm works. So now, beyond this simulation, we apply this data, this algorithm to the corpus data. Let's see what will happen. Right, this the true collaboration network. The left is what we are going to use the algorithm to iterate. So let's see what will happen. So the first three interaction rapidly formulate. And then there are lots of other interaction, much dense, but mostly they are red in the sense that the Jij will be negative. A few of them will be positive, means the Jij will be green. That means Jij will be positive. Positive means that they are more often than average, but the red color means they are less often collaborated than others. So you see the same phenomena as before. From this data, if you run this algorithm, if we run this algorithm without early stopping, then that converge to something overfitting the noise. However, if we early stop that, we can capture some true or faithful interactions between the authors and make some good predictions. So this is the kind of phenomena I want to highlight using this illustration to highlight. And everything we are going to talk about that later is about early stopping, how the early stopping can be used to avoid overfitting the noise and return some true sparsity or say causal relationship between in the models. Okay, so this is the slides that Yanwei already showed you before, and compare this picture compared the Euro stochastic gradient descent method and the training path using the split LBI, decile LBI. I'm going to talk about the math after that, but I think Yanwei already showed that. So the right, that is the filters, important filters selected. That's the convolution filter selected along the split LBI, along the early epochs. So there are three stops at the epoch 20, 40, and 80. So you can see the selected filters are kind of highly concentrated on some particular patterns. However, if you run the stochastic gradient descent, they are not so specific. The filters, basically, there are lots of many different filters. They are kind of dense. This one is kind of sparse. So from compared with previous examples, though this illustrates that those are the most important filters discovered by decile LBI, such that the performance will be the same. With this subnet, the performance accuracy will be similar to the full dense model. So this is the picture for MNIST dataset. However, if you do the same experiment using the ImageNet, the things are much more intrigued because this is on the bottom line, this is the SGD, stochastic gradient descent. On the top line, they are the DESI LBI with 2 different kappa. So you can see they also select some sparse filters, but the most important filters on the top left, the least important will be on the bottom right. So you can see the most important filter is a kind of texture features rather than the color or shapes. Color or shapes will be on the bottom right. So this actually tells you the ResNet 18. This is typical deep network trained on ImageNet. It's not using the clues like human to recognize the image. They are using some high order statistics featured by texture patterns rather than the color and shapes. Those are least favorable in this selection process. Okay, so I think this is somehow trying to give you the idea how the early stopping can be used here to select important feature or causal feature in your models. Okay, so how this kind of picture really, how does it work in theory? Below, I'm going to show you some story from statistical point of view. Basically, that's a statistical model selection consistency under the early stopping regularization. So what I'm going to show is first the simple iterative algorithm in the very beginning, and including other talks EMA showed other type of algorithm. So this simple algorithm shadows a particular kind of dynamics. We call that that's a kind of inverse scale space described by differential inclusions. So they are the special case of mirror descent. If you are coming from optimization society, you can find very close. There are some important particular case for mirror descent algorithm. So in this type of inverse scale space algorithm or dynamics, important features usually are learned fast or faster than the non-important ones. So you see many different examples before what I mean by important or not. They in different application scenarios, they refer to different intuition. And so this simple algorithm, of course, very easy for parallel implementation for large scale applications. And in statistics, we are going to show that in the basic format, this algorithm works under nearly the same condition as lasso in terms of variable selection that reach the model selection consistency if a proper early stopping rule is given. And this algorithm, this dynamics actually can have been less biased than lasso, so that's the advantage. However, if we are equip them with variable splitting, this algorithm can weaken the condition of, say, generalized lasso. So it's more general version of lasso in feature selection. So in that sense, they can be better than lasso in terms of model selection consistency. So this is the rough picture. I hope I can rapidly cover some of the core material without mentioning too much detail. And we basically talk about, when we talk about the theory, it's about two things. One is sparse linear regression. We call the basic sparsity in the sense that y equals to x beta star plus epsilon, and beta star is sparse. Just a few of them will be non-zero. We take the support set to be S, and then complement null set will be T. And another scenario is the generalized structural sparsity or transformational sparsity. It means our sparsity is not on beta star itself, it's on a linear transformation D beta star. gamma star. We call that gamma star. That is a sparse. We call this transformational sparsity or structural sparsity, and also study its support set, gamma star. And both will be useful. And the question is how to recover the sparsity pattern. A statistician call that sparsistency. And so that's the issue. And so the first issue for this kind of question is even you know the support set, true support set, you don't know this one. So if the God revealed support set S to you, then we call the estimator to be the oracle estimator. You can never do better than oracle estimator. That's the subset least square estimation using the support information. So that gives this one. So this oracle property means that you always have model selection consistency because support set is the truth, and the estimator is asymptotic, is a normal subject to normal distribution with the mean equals to the beta star. That's the ground truth, and this is the covariance matrix. And this oracle estimator is unbiased in the sense that its mean is the ground truth, but you never have this oracle estimator because you never know the support S. You have to estimate S in practice. So people usually use lasso as L1 penalized the least square problem. So here I write T as the regularization parameter instead of lambda multiplied by L1 norm, usually used by statistician. But this T is for comparison with inverse scale space to illustrate the idea. And this kind of optimization is very popular in statistics. People usually started using the first order KKT optimality condition, first order optimality condition, 3A and 3B. If you take subgradient with respect of this L1 norm, then that gives 3B, and on the other hand, it gives you the first order derivative mass equals to 0, that's gives 3A. So that characterizes the property. But the well-known issue for lasso, if you solve this KKT condition, lasso is always biased in the sense that you can see a particular example using X equals to identity. That's the identity design matrix with single sample, single dimension. Then the lasso estimator must be this closed form. If tau, this is the regularization parameter. If tau is less than this parameter 1 divided by oracle estimator, then bit hat equals to 0. This is the lasso estimator. Otherwise, this is equals to oracle minus 1 over tau. Tau is a fixed amount. It's a regularization parameter. So this never satisfies the expectation of bit hat equals to beta star. So this is the unbiased issue. So this is by Woutow's picture as the illustration for the bias of lasso. The blue is the lasso solution. It's kind of shrink from the ground truth. And in this kind of scenario, even you know the oracle, even along the lasso estimator on the path, you know at certain path point, you reach the support recovery, you know the oracle support of S. Then the lasso estimate is, in the general case can be written as the oracle estimator minus this is the bias part. This is the red is the lasso bias part. Then the question is how to remove the bias. Can you have an easy way to remove the bias? And in statistics, people develop a non-convex regularization using, instead of using L1 norm, they use a Q penalty, LQ penalty, such that in the general shape like this solid curve, starting from Zhenqing Fan a long time ago. And but this question is it's non-convex optimization. usually it's hard to locate a global optimizer. We have to ask under what kind of condition all the local optimizer gives statistically good estimator. Of course, how to describe statistically good will be an interesting problem. And for another idea comes from applied math. So let's see how this idea developed toward the inverse scale space. So this one, if you start from lasso, take a first order KKT condition, you get this one. Rho t is a subgradient beta 1 norm, and the right hand side is just a gradient of square norm. And if this KKT condition, because both sides depends on parameter t, that's the regularization parameter, we can formally take derivative with respect to t. And the left hand side becomes rho t derivative, right? This is the right hand side. And beta t and t, these are two terms depending on t, so you can take derivative like this. So with this, you can actually have a plug in something. Assume at certain point, say at tau n, t equals tau n, in the neighborhood, we achieve the sign consistency in the sense that rho tau n equals the sign of beta star. So whenever I lies in the support set, that must be plus or minus 1. Otherwise, that's equals to 0. So the rho dot, because it's constant plus or minus 1, then if you take derivative, must equals to 0. So in other words, this one must, if you solve this one at this sign consistency, then the blue part must equals to the oracle estimator. So this actually gives you an automatic way for debiasing. So in other words, if you recall that the previous lasso formula, this is the lasso estimator equals to the oracle estimator minus the bias. So if you plug in this one into this blue part, take the derivative with respect to tau, then you immediately cancel the red part, the bias. You get this oracle estimator. I think this is all the key idea for this, maybe for this tutorial, this theoretical part, because that tells you how to do the debiasing. And this is if you formally write down this idea as this is called differential inclusion. This is exactly give the differential inclusion like this. If you take the lasso KKT condition and the rho dot t, that's the derivative with respect to t. Compare with lasso KKT condition, this one is on the bottom. So this kind of dynamics first arise in applied math called the inverse scale space, because the important feature or coarse grained feature in image recovery appeared first along this iteration, just like various examples we see before, and then the fine detail appears in the later. So these are the firstly appeared in image recovery. But of course, this connection with lasso is from modern statistical point of view. And so here is the solution that doesn't have this bias, and you can see get a closed form solution, debiasing as desired. And to solve this solution dynamics, we can use a sequential restrict maximum likelihood estimate. So that I can skip this. And this is the comparison on the diabetes data with lasso and this inverse scale space. You can see this inverse scale space is piecewise constant rather than piecewise linear in the lasso. However, their order will be the similar. And why the order will be the similar? So here we can share with you a past consistent theory in the sense that there is a nearly the same condition called a incoherence condition for sign consistency of lasso. The solution path contains some particular point, those points which are sparse and sign consistent. And once the sign consistency is met, there must be the oracle estimator, which is unbiased. So that's the kind of thing. And the early stopping is all you need to find such point. So here are the conditions, assumptions to show the theory. We need a restricted strongly convex, means the Hessian matrix of the square laws restricted on the support side must be positive definite. And second, they call the incoherence of a representable condition written in this form. That's the same as Lasso, and the rich literature studied that. And inverse scale space actually is a kind of restrict gradient descent in this sense. So because you have the incoherence condition, and that ensures your dynamics will first go gradient descent in the support set of the of your signal. That's called oracle sparse space, oracle subspace. And because the loss is restrict strongly convex in this subspace, so you have exponentially fast decay toward the saddle point or toward the local minimizer in this subspace. And then the early stopping can avoid you go to beyond this oracle estimate, this subspace. You find this saddle point, that's the oracle estimator, and the early stopping avoid you to go to escape from this subspace to find noise. That's the intuition of this kind of inverse scale space as restrict gradient descent. So mathematically, this is the theory. Basically, that says this is the early stopping time. Before this early stopping time, you won't have a false positive in the sense that you always evolve in the support oracle subspace. And then you find if the signal is strong enough in the sense that the minimum magnitude is larger than this lower bound, then at this early stopping time, you can reach the sign consistency, then you find the oracle estimator. This early stopping time, of course, depends on the incoherence condition eta and other parameter, which is not decidable in practice. But later we can say we can use some data adaptive rule to decide the early stopping toward the false discovery control. But that's the main theory, formalize the idea. And you can design a fast, large scale algorithm from this dynamics. So because the dynamics piecewise constant, you first make it continuous by adding this 1 over kappa damping term. And then use forward Euler discretization, then get this algorithm that's called linearized Bregman iteration in literature, invented by Watao Yin and Osher group long time ago. And so that's the two-line algorithm I written in the very first slides in the beginning. So we can skip that. So here, what's the difference between this algorithm with ASTA? ASTA actually only solve a fixed one penalized problem. So this is the ASTA algorithm that solved the lambda regularized lasso with regularization parameter lasso lambda. And if this iteration goes to infinity, that solve this one. If you want to find the regularization path, you have to take a grade of lambda k, then solve ASTA parallelly and until convergent. However, this linearized Bregman, although looks like quite similar, in computation cost, they are indeed the same. Just a single run of this algorithm that returns the whole regularization path. That's the crucial difference between the ASTA and the linearized Bregman. Okay, so here is the illustration for generate the regularization path and maybe less bias, as I mentioned before. This is the path consistency in discrete setting. I think you can also generalize this to general laws and regularization. I won't talk about too much detail here. The summary about the generalizations. And one thing particularly I want to mention is how about the transformational sparsity? If you have this gamma star equals d beta, instead of beta star to be sparse, gamma star to be sparse, what will happen? And so this is the comparison between generalized lasso and split lasso. So generalized lasso comes from statistics. So this d bit L1 regularization, and the split LBI, this one take a relaxation of gamma minus d beta in the neighborhood, Euclidean neighborhood, instead of exactly d beta. So then apply the linearized fragment on this new laws. So that's the crucial difference. And with this difference, actually, you can show that the new relaxation actually can improve the performance in terms of variable selection. So this table shows that with new increase, actually, you can increase the power of variable selection or model selection. And why this happened? Because variable splitting may induce a weaker irrepresentable conditions than generalized lasso. So that's the key. So I think I may simply skip this one that simply says the necessary sufficient condition for split LVI is called this represent condition, a representable condition and the family of nu that can be strictly lower than the generalized lasso. The IC1 is the generalized lasso condition, and this blue curve is the IRR for nu. If nu enlarge, that could be strictly smaller. Okay, and as a result, you can prove similar statistical path consistency for this kind of condition. And in particular, along this split lasso, you can reach this no false positive property and sign consistency and L2 consistency. And of course, the cost of this enlarging nu no free lunch may increase the L2 error. And you need to project back of this L2 error to the sparse kernel, sparse support set. Then you can recover this min-max optimal rate. So that's the main statistics. I think we have many applications, but we don't have too much time. This is we show this algorithm in the neural network, finding the lottery ticket using early stopping. I think next talk, Xinwei will talk this Alzheimer's disease detection. And finally, as I mentioned, in the very beginning, the early stopping time in our theory is not known in practice because of incoherence condition is not known. But fortunately, we can use a knockoff idea developed by Barbara Candace toward a data adaptive early stopping rule. So if you are interested with this development, you can refer to this our recent paper with another student and Xinwei. I think I can take a stop here. So basically, in this short tutorial, we show you the limit of linearized Bregman iteration follows some differential inclusion of inverse scale space, we call that. And the most important things is significant features emerge earlier on solution paths. And you need some early stopping to avoid overfitting noise. So this kind of dynamics can render unbiased oracle estimator under the sign consistency, the same condition as lasso. But if you use the variable splitting, you can work under a weaker condition than generalized lasso, achieve the sign consistency. That's the main theory. And if you are interested, you can take a reference list to see the more detail. Sorry, I'm over time, but hopefully save some time. I think I should pass it to the Xinwei for the next talk.